To truly understand how bulk materials behave, how water flows, how ice melts, or how drugs dissolve, scientists use molecular dynamics. They map the physical forces acting on every individual atom to see how they behave as a collective. But there is a massive computational bottleneck. A single drop of water contains roughly 1 billion trillion molecules. Even our most powerful supercomputers max out at tracking a few thousand particles at once. You might think we could just simulate a tiny box of 1,000 water molecules and call it a day. But a tiny finite box introduces a serious physical flaw. At that small scale, nearly half of all the simulated atoms end up sitting directly against the outer walls of the box. Molecules trapped at a boundary behave entirely differently than molecules safely inside the bulk of a fluid. They are missing neighbors on one side, which means the physical forces acting on them are distorted, constantly pulling them toward the center. When you run a simulation in a normal, finite box, you aren't calculating the internal properties of a true liquid. You're only simulating an artificial, microscopic floating droplet. To fix this, researchers rely on a topological workaround known as periodic boundary conditions. Instead of a box with hard walls, they treat the simulation space as an infinitely repeating 3D lattice. The rule is simple. When a particle exits the right side of the box, an identical periodic image of that same particle immediately enters from the left. The total density remains constant. But this introduces a new mathematical challenge. If space repeats infinitely, a single particle theoretically has an infinite number of neighbors pulling on it. This diagram shows the solution. The minimum image convention. A simulated particle does not interact with every copy of its neighbors. It only calculates forces against the absolute closest available image of any other particle. Those dashed circles represent the cutoff radius. For the math to stay consistent, this radius is strictly capped at half the length of the box. This ensures a particle never accidentally interacts with a copy of itself. Under the hood, the simulation code executes this spatial math using a simple nearest integer function. When an atom crosses the line, the software instantly subtracts the box length, wrapping the coordinates seamlessly. By mathematically folding space and limiting the interaction radius, researchers can capture the bulk physics of a massive fluid system while only tracking a few thousand data points. The standard cube is the easiest shape to build, but it isn't always the most efficient. Because our interaction rules rely on a spherical radius, the sharp corners of a cubic box represent extra volume that adds to the particle count without actually increasing the effective distance between periodic images. If you shave off those corners, you get a truncated octahedron. This shape is much more spherical and tiles space perfectly. It allows researchers to maintain the same interaction distance with fewer atoms, which is ideal for wrapping around globular proteins. Sometimes, however, the goal is to study an interface specifically, like the surface of a cell. That requires breaking the infinite loop to create what is called a slab geometry. This is a model of a lipid bilayer membrane. It's a flat, planar sheet that needs to be modeled as a nagroscopic surface. To model this correctly, slab geometry retains the periodic wrapping in the horizontal x and y dimensions, allowing the membrane to stretch out forever. But in the vertical z dimension, the boundary is severed with a vacuum gap to isolate the surface. Compare that to this spherical liposome. Because this membrane naturally curves back in on itself to form a closed shell, no vacuum gap or slab geometry is required. The surface is already its own boundary. By manipulating the shape and dimensionality of the periodic boundaries, computational chemists can custom build the exact infinite environment a specific molecular system requires. This topological illusion does have breaking points. If the physical forces being studied are extremely long-range, the simulated atoms begin to sense their own infinitely repeating images, forcing a rigid crystalline symmetry onto what should be a random fluid. The simulation algorithms also struggle with physical scale. If a liquid undergoes a massive structural fluctuation that physically grows larger than the simulation box itself, the periodic boundaries will artificially suppress it. But the most subtle danger of a small repeating box is an artifact called correlated recurrence. Imagine a single atom vibrating sharply. That motion triggers a kinetic ripple, like a sound wave, that propagates outward through the surrounding material. In a small periodic box, that wave travels out the right side, wraps around the universe to enter the left side, and eventually strikes the exact atom that caused it. This creates a feedback loop of artificial physics. To avoid this, researchers carefully expand their box sizes to ensure these ripples dissipate. Despite these artifacts, mathematically folding space remains a vital cheat code, allowing us to bypass the limits of hardware and predict the infinite physical behavior of life-saving drugs and new materials.